Hello, everyone. Come on in. Come on in.
Hi.
Anybody have any pressing questions while we're waiting for everybody else? Nada? I'm double checking my notes, make sure what we did last time. Today's the 9th. Last time was the 4th. Yeah, it looks like I had finished up. I hadn't really finished up relativity, had I?
Yeah, I think we still had some momentum and energy or kinetic energy problems to do.
Yeah, I did addition of velocities, the new equation for that. I did a muon lifetime and showed you how to make it. And then I did a muon length, what the muon thinks the length of their atmosphere was. So yeah, so now I got to do some stuff regarding, let's do an electron, say. So two things that I think are very helpful for starters is to learn this energy method, or this energy unit, which is called the electron volt. You'll definitely cover it a little bit more in section 242 of this course, but it's still something that we use now because we cover relativity and stuff like that. So I'm going to hit you with that real quick and show you a conversion, for instance, for the electron rest energy, what we call its rest mass, if you will, but it's in weird units that are kind of neat. But anyways, I'll do electron and proton just so we'll have those out of the way. So let's go ahead and get started with that. We know that the energy, go ahead.
You said electron rest?
Yeah, rest, R-E-S-T, mass.
Which chapter is this?
We're still on 36, right?
Yeah, it's still 36 relativity stuff.
Because I still haven't completed that homework yet.
Yeah, I just reset some dates, so hopefully they'll maybe help you a little bit. But remember, there is a setup where you're allowed a certain number of days, and you just lose points if you're a little late. I wouldn't go very late though.
Yeah, you didn't post the test. You only posted the practice test, though, right?
Yeah, I noticed that.
Yeah, I think you said they were going to come Wednesday.
Do that. I'm trying to do that right after class to remember this is test 4 and test 5. I remembered right after I went to bed last night. I'm like, oh man, I didn't sit the test yesterday. So yeah, I'll get that.
There were 2 practice tests, right? Because
yeah, test 4 and test 5. And what I'm going to do is test 4. I'm going to go ahead and open up today, and you will have until Sunday to do it. And test 5, I probably am going to open up I might even open up today because it doesn't really matter, but I'm going to give y'all till Wednesday to do that one. Not tomorrow, but the next Wednesday.
Gotcha.
Okay. So
it's on chapter 11, right? It includes chapter 11.
Yeah, it starts with chapter, it might have 8 as a thing, but it's like 8, 9, and 10 or something like that, or 8, 9, and yeah, it might be 8, 9, and 10.
Yeah, the first one is for 8, 9, and the second one's for 10, 11, and 36, I think.
Okay, gotcha.
So we have 2 tests?
Yes.
Okay.
But like I said, the first one's due Sunday, the second one's due a week from tomorrow.
Okay.
All right, so in relativity, we found that, let me turn on my document cam. We found basically the laws of physics are the same as they ever were, but some of the actual equations have changed. So P was equal to mv. Well, P is now gamma mv. And specifically, you can actually treat that as a vector, even though we don't do that much because it turns out to be a 4 vector, where the first component is not x, but the energy, and then the second component is x, third component is y, fourth component is z. So that's a new version. We also found that kinetic energy, oddly enough, is equal to gamma minus 1 times mc squared, which means the energy is actually just gamma mc squared. But it turns out if you play around with the algebra a little bit, that'll show you that E squared is equal to P squared C squared plus M squared C to the 4th. So there's a lot of new expressions we can use. But what I wanted to do is show you how we can express MC squared in terms of mega electron volts or kilo electron volts and stuff like that. And then that'll give us a new value that we can use for energy and for mass for that matter. So it turns out a potential energy can be given by the charge times the voltage. That's something we learned from electricity and magnetism. And I might even show this to you before. But if you take the charge of one electron, that's 1.602 times 10 to the negative 19th coulombs, and you allow that to go through a potential difference of 1 volt, then you get a quantity of energy called the electron volt, and it turns out to be 1.602 times 10 to the negative 19th joules is defined to be 1 electron volt. See how that unit looks like the symbol they normally use for the charge of the electron times the unit they use for, or the symbol they use for voltage. So that's the electron volt. So if you now take the
Is it times 10 to the negative 19 joules?
Yeah, 10 to the negative 19.
Okay.
So if you now take MC squared for the electron, so E rest for the electron, you get the electron's mass is 9.109 times 10 to the negative 31st kilograms times the speed of light, which is 299,792,458, which sometimes I just like to write to keep it in my brain, but that's going to be squared. So when I do all this, I'm going to go 9.109 e to the negative 31 times 299,792,458 squared. And you can see that indeed I did that. And I get 81.868 joules. Now I convert that to electron volts by dividing by 1.602 e to the negative 19. So I just divided that by that, and that gave me, oops. Evidently it didn't take my exponent, so I'm gonna say enter. And that was times 10 to the negative 15th, by the way. Ooh, that's a bad thing. 81.868 times 10 to the negative 15th joules. Now I'm going to divide that by 1.602 e to the negative 19. And that gives me 511.03 times 10 to the third EV. So there's a couple things you can say. The rest energy of the electron is equal to 511 kilo electron volts, or it's 0.511 mega electron volts, or, and this is a weird thing, you can say the mass of the electron is 0.511. Again, you can put the 0.3 on it if you want, MeV per c squared. So that's some of the kind of stuff you could actually do. Similarly, we could do the energy of rest of the proton. And of course, the proton has a mass of 1.670, I think it's 1.6726, sorry about that. 1.6726 times 10 to the negative 28, if I remember correctly. Let's make sure of that. 10 to the negative, oh, glad I checked both of those. 10 to the negative 27 kilograms times, again, 299,792,458 meters per second. That quantity is going to be squared. So I can say 1.6726 e to the negative 27 times 299,792,458 squared. And I get 150.326 times 10 to the negative 12th joules. Again, I'm going to divide that by 1.602 times 10 to the negative 19th. And you can see that I get 938.4 mega electron volts. Notice it came up to 10 to the 6th. Okay. So that's mega electron volts. Now, if you notice the proton, or excuse me, the proton is a little bit lighter than the neutron. The proton has a mass of 1.6726, whereas the neutron has a mass of 1.6749. So you could also do that 1.6749 times 10 to the negative 27 kilograms. And that would be E rest for the neutron. Left off the N and drew a horrible N. Left off the T and drew a horrible N. If I do that, 1.6749 e to the negative 27 times 299792458 squared. That gives me 150.533 times 10 to the negative 12th joules, divided by 1.602 e to the negative 19th. That gives me 939.7 MeV. So you can see that those are, the three main particles that make up an atom, of course, and even now we know the proton and neutron aren't fundamental particles. The electron still seems to be. The proton and neutron, of course, are made of quarks, but these are some masses that we use and some energies that we use frequently. So it's good to have an idea of that. Not only that, it's good to have an idea that you can call the rest energy this in MeV or KeV, and that you can call the mass MeV per c squared. Not only that, you can call momentum MeV per c. So you can convert momentum, mass times velocity times gamma. You can use that same figure and that'll convert it to MeV over c. So that's kind of helpful too. Now, that being said, let's look at some particles. What I want to consider right now is, so this was sort of example 1. Now let's say example 2. So let's say what is the momentum classically and relativistically I knew that wouldn't fit. For a proton with velocity A, let's call this 2.0 times 10 to the 7th meters per second, and B 0.98 C. Okay, so we're going to actually ask for the momentum. Momentum, of course, P classically is equal to mv, so we can automatically calculate that if we'd like. And then, of course, that's going to be 1.6726 times 10 to the negative 27 kilograms times 2.0 times 10 to the 7th meters per second. So this is part A. 1.6726 e to the negative 27 times 2e to the 7 gives me 33.45. Times 10 to the negative 21 joules. Or excuse me, that's kilogram meters per second. All right. So if we wanted to, we could go back and calculate that in terms of, like I said, MeV per c squared or something weird like that. I'll leave it at that right now. Now I'm going to do P relativistically. So P relativistically is gamma times MV. But gamma in this case is going to be 1 over the square root of 1 minus 2.0 times 10 to the 7th over 3.0 times 10 to the 8th. And all of that, of course, times 33.45 times 10 to the negative 21 kilograms meters per second. So we got another student just coming in. So I'm going to take that same 33.45. I'm going to say times parenthesis 1 divided by, I'm going to say square root 1 minus basically 2 over 30.
Would that be 2 over 30 squared or?
Yeah, I'm definitely squaring it. Thank you for mentioning that. I was doing it, but yeah, I didn't say it. So that's a big difference. So in this case, you don't get a huge difference, but you do get a difference, and that difference is 33.553 times 10 to the negative 21 kilogram meters per second. So that's really the unit for, or excuse me, that's really the momentum relativistically. You can see that if you really want to see how far off you'd be by using relativistic or by using classical, you just basically take the difference and divide it by the correct one. So I'm going to do percent error just to give us a feel for what it is. I'm going to say 33.53 minus 33.45 over 33.53. Notice the 10s to the 21s are all going to cancel out. And then I'll multiply by 100 and put a percent symbol on the end. So 33.53 minus 33.45 divided by 33.53 and then times 100 gives me 0.24%. So a very small percentage, and that's because the momentum is really quite small. Or another way of thinking about it is the kinetic energy, which we didn't calculate, by the way, is nowhere near the actual rest energy of the proton. We found the rest energy of the proton was 150.326 times 10 to the negative 12th, or 938.4 MeV. So if we really wanted to do, remember, kinetic energy is equal to gamma minus 1 times mc squared. We already found out what gamma was. If I just subtract 1 from that and then multiply it by 938, you'll see that it's really quite small. So let's do 1 divided by square root 1 minus parentheses 2 divided by 30. Now I'm going to square the 2 divided by 30. And that gives me 1.00223. So gamma is equal to 1.00223. So kinetic energy is gamma minus 1 times mc squared. So that would be 0.00223 times mc squared. So I'm going to say times 938.4. And I see that gives me 2.09 MeV is the energy of that. So the rest energy is 938.4. This is 2.09. So if it's not a appreciable percentage, like at least close to say 10, 15%, then you don't have to use relativity. Okay. Unless you need like the third, fourth, fifth decimal place or something god awful like that. So that's part A. Let's look at part B, and you'll see a significant difference goes on there. So part B, we want to do the same thing, only this time we want to calculate it for 98% of the speed of light. So P is equal to MV becomes 1.6726 times 10 to the negative 27 kilograms times 0.98 times 299. Again, I write all these digits just because I try to keep them fresh in my head. You don't have to. So 1.6726 e to the negative 27 times 0.98 times 299,792,458. And I get 491 times 10 to the negative 21st joules, which I convert to electron volts by dividing by 1.602 e to the negative 19. And that gives me 3.067. And actually it's X electron volts per C. So I'm not even going to mess with that. I hadn't talked to y'all about that yet, but I'd first do that and then I'd divide it by C, the numerical value by C, and that would give it to me. But that's sufficient right there. 4.91 times 10 to the negative 21. And let me put a couple extra digits. I
Wouldn't
know
it
we're
be
not
kilograms times meters per second?
Yeah, thank you. Let me put a couple extra digits. So 0.404. Again, these are extra digits, but in this case, I won't need them like I did in the last case because you'll see a significant difference from the very beginning. And yes, it's not joules, and that's exactly the reason why I screwed up for a second there, is because I called it joules. It's kilogram meters per second. Now that's the classical value. Now the actual value, the relativistic one, is equal to gamma times mv. So I'll do 1 over the square root of 1 minus 0.98. Notice when I write just 0.98, I don't have to put any c's in there at all. I'm just going to take and square that and multiply it by, of course, mv, which is exactly the same thing I got there, 491.404 times 10 to the negative 21 kilograms meters per second. So I'm going to say 1 divided by square root 1 minus 0.98 squared. That gives me 5.025. So you can see that's actually a pretty significant gamma factor. So I'm going to say that times the 491 that I had before. And I got 2.469 40 times 10 to the negative 18th kilograms meters per second. Now, ideally, to really compare these two, so it makes a little sense, I should really want to put them both in negative 21 power. So if I divide this by 1,000, that would make it 10 to the negative 21. Then I have to multiply this by 1,000. So that'd be 2469.4 times 10 to the negative 21 kilogram meters per second. You can see, yeah, that's quite a bit bigger than that. And imagine how bad your calculations would come out if you're actually solving a problem involving momentum, when the momentum you used was 491 instead of 2,469. So you can see at the high velocity end, these momentums can become quite a bit larger. In this case, it's 5.025 times larger, but still, it's just a lot. And in fact, I think today we were talking with some students before this. I had a review session or help session at 8 and had another one at 9. And for instance, at 99.9% of the speed of light, the gamma factor, gamma at 99.9% became 22.33, I think. Gamma at 99.99% became like 70.71%, 70.71, and then gamma at 99.9948 became I want to say 89. So it was like really, really huge. So you can see as closer you get to the speed of light, dramatically huge changes in gamma occur. So any questions on that? Now, again, from the equation, E squared is equal to, so this will be a bar, second bar, P squared, C squared plus M squared, C to the fourth. You can see that really you can talk about P as equal E over C in some sense. So you can see, at least from a unit standpoint, if I take the momentum, I can express it as the energy per C, and that works. So that's what I was talking about earlier. So let me just quickly show you that. Let's say this 2,469.4 times 10 to the negative 21 kilograms meters per second. We're going to express that as basically, if you remember, kilograms meters squared per second squared would be basically joules, because 1 joule is 1 Newton times a meter, and 1 Newton is a kilogram meter per second squared. So if I put another meter there, you get kilogram meter squared per second squared. So really this is off by a meter per second. If I multiply it by another meter per second, then I have units of joules. So that's the same thing that this is telling us, is clearly it's just a energy unit divided by C. So I could call this 2469.40 times 10 to the negative 21 joules per meter per second, like that. Now you can start to make a little bit of sense out of it. I can convert the joules part, so I can say P is equal to 2469.40 times 10 to the negative 21 joules per meter second. And I can say, okay, wait a second, I know that 1.602 times 10 to the negative 19th joules is equal to 1 electron volt. So I can get rid of the joule there, and then I'm left with electron volts per meter per second. So let me do that real quick. And that gives me 15.41448. I'm just carrying a bunch of extra digits here so y'all can verify that you did everything right. So this is going to be 448, and that's just pure electron volts per meter per second, but I want electron volts per C, and that'll cancel out the meters per second. So if I divide it by C, then I'm going to multiply this by C, and I'll say 15.411 times 299792458, and that will cancel out with the meters per second here. So I'll get 4.621144 times 10 to the 9th electron volts per C. So basically all I did was multiply by C and divide by C. The dividing by C I left down there. The multiplying by Z I made this. So you can see this thing actually has 4.621144 giga electron volts per C. And that's the actual unit for momentum. So now you know how to do that as well. This is obviously, at 98% of the speed of light. That's a huge amount of momentum. So that's why it came out so big, GeV per C. Any questions on that one? Okay, now let's do another calculation. This time we're going to do a calculation involving the momentum of that, or excuse me, the kinetic energy of that particle. So example 3, I'm basically saying those MC squareds that I converted, that was example 1. The momentums that I just calculated were 2, and now this is example 3. What are the classical and relativistic kinetic energies of a proton when V is equal to 2.0 times 10 to the 7th meters per second, and V is equal to 0.98 C. So solution again. Kinetic energy classically is 1/2 mv squared, which looks nothing like the relativistic one, by the way. Kinetic energy relativistic is gamma minus 1 times mc squared. Don't even have the doesn't even have the v there, right? I'll show you how those are equivalent in some sense. So we'll say it's 1/2 times 1.6726 times 10 to the negative 27 kilograms times the velocity is 2.0 times 10 to the 7th meters per second squared. That's actually a pretty good size number, but not compared to that 10 to the negative 27th. So 0.5 times 1.6726 e to the negative 27 times 2 e to the 7 squared. And I get 334.52. And that's times 10 to the negative 15th joules, which we can convert to electron volts by dividing by 1.602 e to the negative 19. And that gives me 2.008 mega electron volts. 2.088, sorry about that. Okay. So now let's try the other one. Luckily, we already have MC squared for the electron. That's 938.4. So I'm going to say equals 1 over the square root 1 minus 0.98 squared minus 1 times 938.4 MeV. Like that. And what I'm going to do is say, I did get that gamma factor was 5.02518. Yes, I did. So this is 5.025189. So I just subtract 1 from that. I'll see 5.025189 minus 1 times 938.4, and that gives me 3.778 MeV. So you can see there's a little change in there. not a huge one, but there's, you know, it's enough to be, you know, a whole mega electron volt higher. So that's kind of interesting. Of course, I just did it for 0.98 instead of the other part. So let's call that for part B. This is part A. This is part B. Now I'm going to do, I don't know why I did it that way. I did the same thing in my class the other day, and I guess that's the nature of getting old. So let's say A, kinetic energy relativistic is equal to gamma minus 1 times, again, 938.4 MeV. But in this case, gamma minus 1 is 1 over the square root of 1 minus 2 over 30 squared, which we had actually done that as well. If I remember correctly, that one turned out to be like 1.002 or something, got awfully small. Yes, I did. 1.00223. This is 1.00223. That's what that is, times 938.4 MeV. So 0.00223 times 938.4 gives me 2.0926. Let's call it 9093 MeV.
Did you subtract 1 from 1.00223?
Yes.
Okay.
So let me, since I screwed up the order in which I was doing these, let me show you which one's compared to. So that one's comparing to that one. So you see there is a little difference. It's about 1 in the hundreds place of the decimal. So we'll compare that. Now I can do part B, and I'll use like a line with a slash through it to link that to the proper one, since I got it all jacked up, some crazy stuff. So let's do part B. And this is the classical 1/2 MV squared. I think I was right and close to running out of the page there. Again, this is times 0.98 times 299,792,458 meters per second. Quantity squared. So 0.5 times 1.6726 e to the negative 27 times 0.98 squared times so you can see what I wrote here. 0.5 times 1.67 times 10 to the negative 27 times 0.98 squared times c squared. And that gives me 72.1864 times 10 to the negative 12th joules, which I can now convert to electron volts by dividing by 1.602 e to the negative 19. And I get 450.6. Mega electron volts. Okay, so in reality, let's see. So the first part, part A, we were doing classical for 2 times 10 to the 7th meters per second. That gave us 2.088 MeV. And then relativistic for part A, that gave me 2.093 MeV. And then doing relativistic for this, I got 4 times. That's got to be a mistake. I think I misread that. Let's see. 5.025189, 5.025189 minus 1, and then times 930. Yeah, that's definitely wrong. Ah, there is the problem. I didn't see a little exponent up here. That makes a big difference. So it was actually 3.778, and then I didn't see this times 10 to the third MeV. So that's actually equal to 3,778 MeV. That's what should be compared to this. And you can see this is about half of 1,000. That's almost 4,000. So clearly, relativistic corrections make a big deal when you're at 98% of the speed of light. Any questions on that? Okay. So some of the things we talked about, we got some time left now. We're finished with relativity, really. But some of the things we talked about this morning that students were having problems with were problems where they were deriving the Lorentz contraction, length contraction formula from the Lorentz transformations. So I just want to remind you a couple things about that. Our Lorentz transformations are based on the Galilean transformations. Only the difference with the Galilean is there's no such thing as T and T prime. They're both the same. So Galilean coordinates, if you had a coordinate system sitting still, call it S, and it had an x-axis parallel to the other one's x-axis, and in fact at t equals 0, the origins were the same, then you could have an x prime coordinate system, y prime coordinate system that we call S prime, and that happens to be moving with a velocity v. So this little x prime right here is only x prime in this coordinate system, but that same position is x prime plus vt. So Galilean relativity would say x is equal to x prime plus vt, and there would be no prime on t because that's just time is universal in the Galilean worldview. So the y would have no changes, the z would have no changes, and t would have no changes. When you go to the Lorentzian transformation, you get x is equal to a gamma pops in, x prime plus vt, and a prime pops in. Y is equal to y prime, z is equal to z prime, and then t gets complicated too. There's a gamma popping in, but there's also a plus vx prime over c squared. If you want to solve this for x prime, y prime, z prime, and t prime, then this becomes, I'll do it with a different color pen, then this becomes x prime is equal to gamma x minus vt, y prime is equal to y, z prime is equal to z, t prime is equal to gamma t minus vx over c squared. So notice all you really did was change v to negative v and going from here to here, and you changed prime to not prime. Okay, so keep that in mind because they give you some problems, and like one of them, they ask you to find out what x is at a particular point in time, but they gave you time in the S frame, not in the S prime frame. And of course, you can find out what the x is, or this way, you can find out what the x is, but not if you have t prime. So you first have to solve for t prime. And once you solve for t prime, then you can plug it in here to get x prime. So that's one of the problems that your homework is requiring you to do that I think a lot of people are missing. So hopefully that's enough of a hint to get you through there. So I'll go ahead and call it a day. It's not enough time to really get started on, well, actually, we got 30 minutes. Yeah, I think I can do a little bit of chapter 11. So let's go ahead and get into chapter 11. Anybody have any questions on that stuff before we begin? Okay, so chapter 11. Now, the good news about chapter 11 is we've more or less already begun it, because if you'll notice, when you look through chapter 11, you'll see some problems like the complex Atwood machine, where you had a massive pulley as opposed to a massless pulley. Right? We already solved that problem. And you also had, for instance, a smokestack with a center of mass up here falling over. That's covered in chapter 11. So we've already done that stuff. The main thing chapter 11 is really about is Newton's second law, summation forces equals mass times acceleration. Remember, that became the summation of the torques is equal to I times alpha. Okay. Which you could also look at as I times d omega over dt, which you could also look like, now this is backwards because actually Newton stated it as a derivative of all of this. So in this case, I'm taking the special case where I is a constant and pulling it inside, but in reality, the final result is the right one. So I get d by dt of I omega. So the real version is the summation of the torques is equal to dl dt, and that's angular momentum. Okay, but this also is another version of angular momentum. So what you can see is if the summation of the torques equals 0, then we have dl dt is equal to 0, which means L is equal to a constant in time. So that's conservation of angular momentum. Now that can translate into I1 omega 1 equals I2 omega 2, or it can translate into this L, where L is equal to R cross P, such that R1 cross P1 is equal to R2 cross P2. So maybe the vector that emanates from the center of rotation or revolution to the object, the particle of momentum P1, changes so that the momentum P1 also changes. Then you get a R2 cross P2 that is in fact equal to the first one. So that's a couple different ways you can see it happening. And in fact, you can say the L of a system, the angular momentum of a system, is actually the summation of over I of R sub I cross P sub I. So you got R1 P1 plus R2 cross P2 plus R3 cross P3, so on and so forth. Well, that has a similar equation where dl dt is equal to 0 for the system, in which case all those things add up as well. So those are all fair. So just as a reminder, let me show you what is L. So if we're talking about L as being R cross P, then that means I put I hat, J hat, and K hat in the first row of a matrix. And then I put RX, RY, RZ in the second row. And then I put PX, PY, and PZ in a third row. Then when I do that, I get, again, a bunch of different ways you can do this, but I'm going to go ahead and just write it out. I'm going to get RYPZ minus RZPY in the I hat direction, plus now we're going to do the J hat direction. So I'm going to get RZ PX minus RX PZ in the J hat direction. And then finally, RX PY minus RY PX in the K hat direction. So that's what our angular momentum vector is. In fact, this is one of the problems that your book has. I think your book has a problem like it, I should say, at the end of the chapter. So that's a common example of what you should be able to do. So given any vector Rx, Ry, Rp, or Rz, and any momentum vector Px, Py, Pz, you should be able to write out the angular momentum in vector form this way. We should also be able to do something like, imagine this. Let's say a disk has a radius r and a mass m, and it's rotating with an angular speed omega equals, let's say 2 pi radians per 0.001 seconds. So 1,000 revolutions per second is basically what it's doing. Remember, because a radian is, or 2 pi radians is 1 revolution. So this does 1 revolution every 1,000th of a second. That means it must do that 1,000 revolutions in a second. Let's say this mass is in fact 1.00 kilograms, and let's say this radius is in fact 10.0 centimeters. Okay. And now, as it's spinning like that, I'm going to drop a blob of clay, a small blob of clay, whose mass is actually equal to 0.25 kilograms. I'm going to drop it right on a distance out of 5.00 centimeters. And I want to know what's the omega 2. In other words, conservation of momentum might not look like it holds here, conservation of angular momentum, because there's clearly a force acting on this disk as a result of this clay. But if I take the system to be the ball of clay plus the disk, then the force the clay puts on the disk is just an internal force. So it's perfectly fine. So in fact, the initial momentum, L1, is actually equal to 0 plus I. I is 1/2 mr squared. That's the moment of inertia for a cylinder, times omega. So I omega is really what it is. We've got what omega is. We got 1/2 mr squared. We got everything we need to calculate here. Now afterwards, L2 is equal to now this thing and the other blob. So we have m, let's say m times r over 2 squared. That's really what the I is for this guy, plus 1/2 mr squared. All that times omega 2 is the final angular momentum. Does that make sense to everyone? I said this blob isn't that big, so I'm treating it like a point particle. So a point particle out of distance r over 2 has a momentum given by m times r over 2 times omega, of course. The I being m r over 2 squared. So now I can say L1 is equal to L2. I get 1/2 of 1.00 kilograms. I'm going to put in the numbers here and just solve it. This will be 0.100 meters squared times 2 pi 000. So that's 2 pi times 1,000, basically, radians per second, is equal to, in this case, I'm going to say 0.250 times 0.05 kilograms there, meters there, squared there, plus 1/2 1.00 kilograms, 0.100 meters squared times omega 2. So omega 2 is going to be equal to, I'll figure out this stuff first. So I'm going to do 0.5 times 1 times 2 times pi times 1,000. Oops. I did 1/2 times 1 times 2. Oh, I skipped the 0.1 times 0.1 squared. That gives me 31.4159. And notice the units turn out to be kilograms, meters squared per second. Radians just drops whenever you want it to. Okay, so that's the omega-2 numerator part. Now I got to divide it by all this junk, which is 0.25 times 0.05 squared plus 0.5 times 1 times 0.1 squared. So I get 5.625 times 10 to the negative third. And these units turn out to be kilograms meter squared. So you can see that I just get radians per second. So I'm going to do that top number divided by that last number. And I get 5.58. 1 times 10 to the negative, or excuse me, times 10 to the third. Sorry about that. Radians per second. So how does that compare to pi? Well, so omega-2 is basically, let's see what 5.5851, how that compares to 2 pi. So I'll do 5.5851 divided by parenthesis 2 times pi. That gives me 0.888. So this is 0.888 of 2 pi times 1,000 radians per second. So it slowed down to about 88% of its original speed, because its original speed was 2 pi times 1,000. Does that make sense to you guys? So that's a typical conservation of momentum problem. I'll call that example 4. Let's do another problem. Let's say example 5. Let's say we have a coordinate system right here. This is my x coordinate system. This is my x-axis. This is my y-axis. And let's say I come up here to a distance of y equals 3.00 meters. And then I go back here to a distance of x equals negative 4.00 meters. And I put a mass m equals 0.250 kilograms, traveling with a velocity v equals 100 meters per second. Okay. What I would like to know is, what is the linear momentum with respect to the origin? Well, the linear momentum with respect to the origin is r with respect to the origin crossed with p. So I got to make a vector that points from the origin to it. So let me draw that real quick. So that's my r with respect to the origin. I think you can see that is basically going to be x I hat plus y j hat, right? Where x is that negative and this is the y, right? And then I can see that P is equal to M times V. Well, 0.25 times 100 is 25. So I'm going to say 25.0 kilograms meters per second in the I hat direction. Or I could just say it's MV I hat. Now I got to take the cross product of those two. So L0 is equal to, somebody have a question?
Yeah, why is your R not -4 I hat plus?
It is. I'm just putting it back in symbols so I can sort of get you a general answer, and then we can plug the numbers in and get the exact answer. But by plugging the symbols in, you'll get an answer that always works.
Okay, that makes sense. Thank you.
No problem. So I hat, J hat, K hat. And then of course the R we can see is just X, Y, 0. And then of course the P we can just see as M, V, 0, 0. So when I do the I component, the X component, in other words, 0 minus 0 happens, so nothing happens there. When I do the J component, I get 0 minus 0, so nothing happens there. But when I get the K component, then I do X times 0, 0, but I just get M times V times Y in the K hat direction. That's what I wanted you to see. See, the Y is the perpendicular distance. So whenever you have something running like that, if you can find the perpendicular distance from the center of rotation to the line that it's traveling along the trajectory, then it's just that times the MV. That's the whole reason I put that in symbols. So now we can say that's equal to M times V was 25.0 times 3, so that's 75.0, and that's kilograms meters squared per second. Any questions on that? So that's actually a very much like a problem that your book has in the, I think it's in the end of the chapter as well, but I just want to make sure you know how to do that kind of stuff. Another thing that's kind of neat is, remember Kepler's laws of motion basically said that when a planet is closer to the sun, it's going faster than when it's farther from the sun. So what I thought I'd do is let you see an example where we work out the perihelion and aphelion velocities of some planets. So let's say example 6. Now example 6 is consider Earth and Pluto. Their perihelion and aphelion distances are, so it turns out the aphelion distance for, I wrote this somewhere, oh yeah, the aphelion distance for Earth and the perihelion distance for Earth. So we want perihelion and aphelion. So first I'm going to do Earth. So D aphelion is actually equal to 1.016 AU, and D perihelion, that's when it's closest to the sun, is 0.98329 AU. And then for Pluto, the aphelion distance is 48.023. AU again. And the perihelion distance is 30.151. If the Earth's perihelion, or excuse me, yeah, perihelion speed is 30.29 kilometers per second, what is its aphelion speed? So that's part A. Part B, do the same for Pluto, whose perihelion speed is 3.71 kilometers per second. Okay, does everybody understand the problem? So what we have, if I just draw a generic orbit that's supposed to be an ellipse, it should look something like this. It'll have the sun right here. This is the perihelion distance. This is the aphelion distance, like that. And notice in this case, the R, in this case, the R, so this is R aphelion, this is R perihelion. They're actually in both cases perpendicular to V. So this would be V aphelion, and this would be V perihelion. So they're actually perpendicular. So that means L equals R cross P just becomes R times P. Okay. And of course, P is just MV, so it's just R times M times V. So when I do Earth, I'm going to say L aphelion is equal to L perihelion. This is part B. This is part A for Earth. So what I'm going to do is I'm going to say the aphelion distance is 1.0167 times the mass of the Earth, which we indicate with a plus symbol in a circle, times the aphelion distance velocity, which we don't know. Well, that's equal to, in the other case, we get 0.98329 times the mass of the Earth times the aphelion, or excuse me, the perihelion distance velocity, which is 30.29 kilometers per second. So you can see that velocity at aphelion, notice these M's cancel out, is just going to turn out to be 30.29 kilometers per second times 0.98329 over 1.0167. So 30 times 0.98329 divided by 1.0167. And that gives me 29.49, or excuse me, 29.29 kilometers per second. So as you can tell, like Kepler said, when they're closer to the planet, to the sun, they are faster. So it's going 30.29 here. Over here, it's only 29.29. So that suggests, of course, that the aphelion and perihelion distance are pretty close, which is why for so long so many people thought it was a circular orbit, because there's really not much difference between the circle and ellipse when the semi-major axis is fairly close to twice the radius. Okay, so now we look at part B. Do the same thing for Pluto, which of course is no longer a planet, but still LA equals LP. We're going to get, in this case, a much more drastic effect. So we're going to have what, 48.023. That's the distance times the mass of Pluto, which I'll just call MP, times the velocity that we don't know. So this is, oh, that's supposed to be A. Sorry about that. Oh no, it's supposed to be P. Duh. I said the aphelion mass, like its mass is changing. Okay, so this is V at aphelion. Now over here I have 30.29 astronomical. No, it's 30.151. Got my numbers mixed up. 30.151 astronomical units times the mass of Pluto. Now I do happen to know the perihelion velocity of Pluto is 3.71. Notice how much slower it is too. Kilometers per second. When the orbit's really, really big like this, you don't have to be that fast to keep gravity at bay. So in this case, I'm going to get the velocity at aphelion is actually equal to 3.71 kilometers per second times 30.151 over 48.023. And I get 3.71 times in this case, I got 2.33 kilometers per second. Actually, I looked those up, and the aphelion velocity of Earth was 29.29 meters per second, so we nailed it. And the aphelion velocity of Pluto actually was quite a bit different. I used 3.71. I did use 3.71. I used 30.127 and 30. I'm wondering now if this was a 6, because I can't read my own writing. Maybe a 6. But either way, before I had 6.10, so that's what makes me think that might be a 6, but actually that would make it smaller, so that's not it. So yeah, the problem with Pluto is Pluto actually has a very, very eccentric orbit. So I'm not necessarily surprised. I'm a little bothered by it, but not necessarily surprised because it listed that. But I could have also recorded it wrong. So there's a whole bunch of scenarios, but it does make sense. It definitely went down. That's the key thing, is to understand that when it's close, it goes fast. When it's far, it goes slow. Not only that, even though that's not what Kepler was talking about in his second law, it actually applies in the case of planets in general, specifically saying planets that are close to the sun go fast and planets that are far from the sun go slow. Again, that's not what Kepler's second law was talking about, but it happens to be consistent with that. So that's a good little mnemonic for you to help you remember which planets go faster, Mercury or, for instance, Jupiter or Saturn. So any questions on that? Believe it or not, that's more or less all the type of examples I wanted to work for you for this chapter 11. So I think it's pretty good. I'm actually considering this being done with chapter 11. If I think of a couple other more things, I might do it. But notice I did last night go in and change the due dates on a lot of mastering homeworks. So I will do my best to make sure they're all right, but y'all can let me know as well. I did set all of the extra credits to be due on at 11:59 p.m. on December 15th. The last day of class is December 17th. So hopefully that should work out. Any questions for anyone?
If we don't have time to finish the extra credits, will we get penalized for not completing them?
No, they're all just points added. So what happens is at the end of the semester, I average up all the required ones. And what I end up doing is basically, I'll say, I'm going to drop your lowest 10 if I have 10 extra credits.
Okay.
Are the practice tests included in that?
The practice tests have another way of counting. Basically, I take your average of all your highest practice test grades and divide it by 20, and that number of points is added to your final grade.
Okay.
Anybody else? All right, well, you folks are free to go. I'll see you again Thursday or in lab before then, possibly.
Thank you.
No problem.
Thank you.
Thank you, Professor.
Thank you.
Those are-
Anybody have a question? Gerald?
Me.
Tristan?
Has nothing to do with class, really.
Okay.
It has to do with the, Jared, do you have something?
No.
All right, I can take you to a breakout room if you want to talk something private, Tristan.
It's not a private, it's just I have a question about relativity.